How to graph y equals f of the quantity k times x, where k is some constant. We're going to compare and contrast graphs of functions in these forms and look for patterns. We're going to see and learn why the graphs are shaped as they are. This is part of the Family of Functions series. You will need graph paper, or you can download this PDF and print it, and please press pause anytime as needed throughout this video. Let's investigate the absolute value function. We're going to compare and contrast the graphs of these functions right here, using technology at first for you to discover the patterns. Please notice that the parent function is in solid red. The transform function is going to be in dashed blue. And this is the slider. We're going to use the slider A, the variable A, to control the coefficient of x here. So right now they are identical. But when I increase A to 2, this is the absolute value of the quantity 2 times x. Notice how it compares to the absolute value of x as A increases to 3, and then 4, and 5, and 6. Now let's go ahead and decrease that coefficient and watch what happens as that coefficient decreases. Look for patterns. Let's look at the graphs side by side and notice that the entire graphs are not shown. These graphs have limited or restricted domains and ranges. So what you see is what you have right here. As the coefficient of x increases from 1 to 2 to 3 to 4, what is happening to the graph? Press pause to think about your answer and then resume. Well, one way to express it is the graph is getting narrower. We'd like you to list the visible limited domain and limited range for each of the graphs. So for example, we'll do the first one here together. So for the visible limited domain that we see, the domain are all real numbers between 12 and negative 12 inclusive. We could write this with set notation or use this bracket interval notation, which we'll use most of the time from now on because it's shorter. The range then are the real numbers from 0 through 12 inclusive. And we could write it this way using that bracketed interval notation. So for the other graphs, go ahead and list the limited domain and range that you see here. Press pause as needed. Press resume when you're ready to look at the answers. So for this one, f of 2x is the absolute value of 2x. Notice its domain, how it compares to the domain of the original and the range. For the red one, absolute value, y equals the absolute value of 3x. Look at the domain compared to the original. Look for patterns here. And then y equals the absolute value of 4x. Look at the domain and range there. Looking for patterns. So using the pattern that you've observed, what would you expect the limited domain and limited range be for the graph of y equals the absolute value of 6x? Press pause as needed, resume when you're ready. So hopefully you said that the domain would be from negative 2 to 2 inclusive, range 0 to 12 inclusive. So that we can verify this, let's go ahead and look at the graph of this right here. Here's the graph of y equals the absolute value of 6x. And you can see the domain is from negative 2 to 2 inclusive. And the range is from 0 through 12 inclusive. All the y values are in there. Let's generalize our findings. This is what we want to do, is look for patterns and then generalize. In the graph of y equals f of the quantity k times x, where k is the coefficient, the absolute value of the quantity k times x, as that coefficient gets larger, the graph gets what? And if you said narrower, you would be correct. The limited domain gets smaller. while the limited range remains unchanged. So we will talk about what doesn't change as well. Another way to word this, in the graph of this y equals the quantity, absolute value of the quantity k times x, as the coefficient k gets larger, the graph compresses in the horizontal direction, compresses, while the range remains unchanged. Another way to say it is we could say it's a horizontal shrink as k gets larger. Going in the other direction, if we start from the right going to the left, as the coefficient goes from 4 to 3 to 2 to 1, as k gets smaller, the graph is what? Expanding in the horizontal direction, getting wider in the horizontal direction, while the limited range still remains unchanged. We also call this a horizontal stretch. Press pauses anytime to catch up. How does the value of k affect the domain? So when k is equal to 2, the domain is half of what it was before. When k is 3, look at what the domain is. It's 1/3 of what it was before. And when k is 4, the domain is 1/4 of what it was before in the original parent function. Looking for patterns. Now we can generalize. For any value of k, the limited domain is what? Press pause as needed. Press resume when you're ready to look at the answer. So the limited domain is the reciprocal of that, 1 over k of what it was. So for example, it was 1/2 when it was 2, 1/3 when it was 3, 1/4 when it was a 4. The horizontal dilation factor is 1 over k, the reciprocal of k, 1 over k. It's a big deal, by the way. We can also say that the value of k is inversely proportional, for that phrase before, to the domain or width of the graph. Now, inversely proportional, what's that mean? It means as k gets larger or increases, the domain decreases, or that width decreases. And as k decreases or gets smaller, the domain or width increases. That's what we mean by an inverse proportional, go in different directions. So the previous investigation was using the absolute value function. Do our results hold true for other functions? We're going to investigate further, again using technology. So using technology, we're going to investigate the quadratic function and compare and contrast graphs in these forms. You ready? Here is our parent function, y equals x squared, in solid red. The transformation function is going to be in dashed blue, and this is our slider. So right now, you can see that these two functions are identical, but let's increase the coefficient to be 2, and so this is the graph of y equals the quantity of 2 times x squared compared to the parent function. The quantity of 3 times x squared, coefficient is 4, it's 5, it's 6, and so you're looking for patterns. And also, if I decrease this coefficient, watch what happens to the graph as we go from the quantity of 6 times x squared to 5 times x the quantity squared, and so on. We're looking for patterns. Now let's look at the graphs side by side, and you'll notice that the entire graphs are not shown. They have limited or restricted domains and limited or restricted ranges. Okay. As the coefficient of x gets smaller, decreases, what is happening to the graph here with this absolute value? Press pause as needed. The graph is getting wider. So what we'd like to do is list the limited domain and limited ranges for each of these graphs. So we'll do the first one together. So if you look at this one, the limited domain is all real numbers between -4 and +4 inclusive, shown like this in bracketed interval notation. The limited range from 0 to 4 inclusive. So let's go ahead and do that for the rest of these graphs. List the limited domain and range as you see them in the pictures here. Press pause and resume when you're ready. For the absolute value of 1/2 x, the domains from -8 to 8 inclusive, range is the same. Absolute value of 1/3 x, the domains from -12 to 12 inclusive, range is the same. And for absolute value of 1/4 x, domain from -16 to 16 inclusive, same range all the way around. Look for patterns. Using the pattern that you observe, what would you expect the limited domain and limited range to be for the graph of f of 1/5 x, which is the absolute value of 1/5 x? Press pause, resume when you're ready to answer. So we'd expect the domain to be from -20 to 20 inclusive, the range 0 to 4 inclusive. And how could we verify that? Is we could just show you the graph and see that the domain is from -20 to 20, all the x coordinates, and the y coordinates go from 0 through 4 inclusive. Generalizing our findings as we did before, in the graph of y equals the absolute value of k times x, where k is now a fraction between 0 and 1, as k gets smaller, the graph is getting wider, the limited domain gets larger or wider, while the limited range remains unchanged. Another way to word this, in the graph of y equals the absolute value of some constant times x, as k gets smaller, going from 1 to 1/2 to 1/3 to 1/4, the graph expands in the horizontal direction, while the limited range remains unchanged. Sometimes we call this a horizontal stretch. How does the value of k affect the domain? Well, when k was equal to 1/2, as it is here, the domain is twice as big as what it was before. For this graph here, when k was 1/3, the domain is 3 times what it was in the parent function. And when k is 1/4, the domain is 4 times what it was. Look for patterns. Generalize for any value of k, the limited domain is, press pause, resume when you're ready. One over k times what it was. We can also say the value of k is inversely proportional to the domain or width of the graph. Remember, inversely proportional means that as k increases, the domain decreases, and as k decreases, the domain increases, kind of a reverse, inverse. So now let's go ahead and investigate some generic function. We're going to compare and contrast graphs of these for some generic function using technology. The graph of this generic piecewise function is in solid red. The transform function is going to be in dashed blue. So this is f at 1x, which is identical. I'm going to increase the coefficient to 2. This is f of 2x. Notice how it compares to the parent function. F of 3x, f of 4x, 5x, and 6x. And notice the patterns you see there. Now let's reverse the order. Let's have the coefficient decrease from 6 to 5 to 4. And notice what's happening to the graph. Look for patterns. All right, let's summarize our findings here. Let's look at y equals f of the quantity some number times x. First of all, when the coefficient is greater than or equal to 1. So look at this. You're going to have to pause this several times so you can let this sink in. As k increases here, the graph compresses in the horizontal direction. And as k decreases, goes from 4 to 3 to 2 to 1, the graph expands in the horizontal direction. We also say this is a horizontal shrink when this happens. When it compresses, it's a horizontal shrink. And when it expands, we sometimes say this is a horizontal stretch. So please press pause to let this all sink in. Resume when you're ready. Here, y equals f of some number times x, where a k is a number between 0 and 1. Here along the top, We're going from f of 1/4 x to 1/3 to 1/2 to 1x. So the value is increasing each time. And notice what is happening to the dashed function. As k increases, the graph compresses in the horizontal direction. As k decreases, goes from 1 to 1/2 to 1/3 to 1/4, the graph is expanding in that horizontal direction. And again, this is the compression is sometimes called a horizontal shrink, and the expansion is sometimes called a horizontal stretch. Again, press pause so this can sink in. Resume when you're ready. I do have a quick assessment, 2 problems here. If the domain of some function is from -6 to 6 inclusive, what do you expect the domain of y equals f of 3x to be? Press pause as needed. Resume when you're ready. Since there's an inverse relationship between k and the domain, as k increases, the domain decreases. So it should be 1/3 of what the domain was before, 1/3. So that should be from -2 to 2 inclusive. If the domain of y equals g of x is from -12 to 12 inclusive, what would you expect the domain of y equals g of 1/4 x to be? Press pause and resume when you're ready. Again, an inverse relationship exists here. So the inverse of 1/4 is 4, multiplication inverse. So it should be 4 times what it was before, which is -48 to 48 inclusive.